All right. Now we're going to move on to the case of Newton's second law that involves the direction of an object's velocity changing. So remember that Newton's first law states that if the forces on an object are balanced, then the object moves at constant velocity. So again, that's not speed, that's velocity. So for an object to move at constant speed and direction, there must be no net force. So as a result, Newton's second law also tells us that there must be a net force if an object's direction is changing, because direction is incorporated into velocity. So the simplest case of this occurs when an object doesn't change its speed, but instead the only change in velocity comes from direction. So we're basically saying the velocity arrow has the same length all the time, it just spins around. And as a result, you'll be tracing out a circle. So this is a special case of circular motion known as uniform circular motion. And as the name implies, it is motion around a circle, and the uniform tells us it is constant speed. And we have lots of interesting properties we can derive from this uniform circular motion. Now, the obvious one is that if you're in a circle, the radius of your path is constant. And also, by definition of uniform, the speed must be constant. But also realize that means v is not constant because the velocity vector is changing. Right, to point in opposite directions on opposite sides of the clock right there. Also, the magnitude of the object's acceleration is constant, but the vector itself is not. And the object's velocity and acceleration are perpendicular at all times. And the acceleration will always point towards the center of this circular path. So we can see why this has to happen, because acceleration is the direction of velocity change. So if the acceleration was directed anywhere parallel to the velocity vector would get longer. If the acceleration vector was directed anywhere opposite the velocity vector, the vector would get shorter, so speed would decrease, meaning the only way that we can be changing direction is if the acceleration does not point with the velocity or does not point against it, meaning it's perpendicular. And we will see that this acceleration is always directed towards the center of the circle in uniform circular motion. The non-uniform case is different, but of course we will cover that. So since this motion is cyclic, we will define the period, capital T, of just how long it takes to go around the circle, because that is a predictable constant quantity. Because if you're going the same speed or on the same distance, it's going to take you the same time to do a lap. Now, I don't know if this is necessarily important to memorize. This is a derived equation on the sheet, but realize that since our speed is constant, we can just write distance equals speed times time, and then we can just solve it for time. Because you are going the same distance every second, even if it is on a curved path. So we can just use constant speed kinematics here. And the substitution we can make, because we're on a circle, is that d is 2 pi r due to us traveling a circumference. So usually capital T is used to denote a period of revolution or a lap time. And also we can define something known as the frequency, which is not how long does it take you to do a lap, but instead it's how many laps are you doing every second. And that doesn't make sense for a lot of motions that are happening slowly or over big radii, but for smaller scale things, we are interested in this. So the frequency units will be 1/seconds, because it's 1 cycle per how many seconds. And we define that as a hertz, Hz. So we'll just start. A runner is traveling counterclockwise around a circular track of radius 64 meters at a constant speed of 3.14 meters per second. How interesting. What an interesting value of speed I chose. So we want to draw qualitatively accurate velocity and acceleration vectors for the runner at each of the indicated points. Well, the velocity vector will always be tangent to the circle, because that's the way you're currently going. And the acceleration will always be directed into the center of the circle, perpendicular to velocity. So, which way are we going? Counterclockwise. So, we can just try our best here to make arrows of the same length, showing us tracing around the clock. So that would be our velocity after I fix my pen here. So again, we know velocity has to be tangent because we know the shape of the path. And then for the acceleration, it is always going to be directed towards the center of the circle. And why is that? Well, again, we just argued that we know the acceleration can't be tangent to the circle in any way, or else the speed would change. So we know it's either out or in. And you can think of this acceleration vector as sort of the way that the velocity vector is going to be rotating at a certain point. All right, what's the time required to complete one lap? Well, we could just use the equation directly, but again, it's constant speed, which is really important to note. This is constant speed. So we can just say distance equals speed times time. And since we are on a circle, that distance is 2 pi r. So we can just say 2 pi r would be equal to vt. So t would be equal to 2 pi r over v. And we can see why I chose my speed to be that value. The radius was 64 meters. So 128 seconds. And I'm sure I made this a reasonable running speed. So it takes the runner 128 seconds to complete a single lap. So now we want the frequency at which the runner completes laps. So this is not a usual metric we're given, but we defined it. So once you have period, it's really easy to convert to frequency or the other way, because frequency is just defined as cycles per second. So if we did this with units, we'd be doing one cycle every 128 seconds, meaning our frequency would be 1 over 128 hertz, or cycles per second, or just per second. And I'll compute what that is. That's like 0.008 hertz. So every second the runner completes 0.008 of a lap. Determine the new time required for the runner to complete a lap at the same speed if the radius of the track is doubled. Well, multiplier time. Distance is still equal to speed times time. And the radius of the track is doubled. So it might help to note that the distance is the circumference, so 2 pi r is equal to vt. We are fixing the speed. And it says the radius of the track is doubled. So in order to double the left-hand side, I must have to double the right-hand side, so the time got doubled. So the new period is just exactly the old one times 2. 128 times 2, that's 256. So just a nice linear relationship there. So if we don't have constant speed, we actually can have two accelerations. So we will still have an acceleration that's trying to turn you and keep you moving in a curved path, but there will also be a tangential acceleration, tangent or anti-tangent to the circle, that serves the function of speeding up or slowing down. So this sort of acceleration that we've been dealing with that turns an object is known as centripetal acceleration, because this is the sort of acceleration responsible for circular paths. So a centripetal acceleration always points perpendicular to the object's path towards the center of curvature, or just the center of the circle. And the total acceleration is going to be just the vector sum of the perpendicular and parallel components. So for example, if I'm traveling around a circle and I'm speeding up, I would have a speeding up tangent component and a turning me perpendicular component, so the magnitude would just be given by the Pythagorean theorem. So anytime we split things up into parallel and perpendicular components, that of course gives us a nice right triangle to deal with. Although this is not a very common thing to have both of these. We do actually have an expression for centripetal acceleration, and the centripetal acceleration of an object in magnitude is just the square of the speed at a given time divided by the radius of the path at that time. So this should make sense that if you're traveling faster, the turning acceleration is greater at a given curve. Then also at constant speed, if you take a curve sharper, that decreases r, so your acceleration increases. So this is the acceleration that you sort of feel when you're in a car turning, especially on a roundabout. If you take a roundabout at faster and faster speeds, you feel that acceleration more. Because again, people can't really feel velocity, right? That's not something we can feel because of the equality of reference frames, right, and forces. But what we can feel are accelerations. So that's how you know you're accelerating, even at constant speed, because you can feel that sort of turn. So let's prove this. So let's say an object moves at constant speed, v, circle, radius r. We want to draw similar triangles that represent the change in position, delta s, because I don't want to reuse r, I guess, and change in velocity of the object while traveling through a small angle. So we're going to assume that for small angles, which is where we're going to zoom in on, because we want the acceleration at a point, so we should be zooming in to small angles. This just kind of exaggerates the picture. So since we're moving in a circle, we definitely know that the radius is constant, and it's going to be r in both of these cases. And then the change in the object's position is just going to be roughly equal to this straight line. And notice it's not a straight line on the circle right now, and that's okay because it looks curved because we have a pretty significant angle in there. So as we shrink that angle, the error we get by approximating the curve as a line is less and less and less. So this gives us sort of our first triangle, where we have an included angle theta. We have two sides labeled r, and then we have delta s across from the theta. So now we got to think about what the velocity would be doing at each of these points. So for the velocity, we know that velocity is going to be perpendicular at a given point. So this would be a velocity, right, and tangent to the circle, and this would also be a velocity tangent to the circle. So we can actually draw a little velocity triangle here as well, where I could get, and we know it is constant speed, so I could get a velocity vector of length v. Let's stack them actually. We could get a velocity vector of length v, then it's going to rotate a little bit. I should make them the same length. And then that means that my change in velocity would therefore be this sort of remaining side of the triangle. And by similar triangles, if this side is rotated 90 degrees and this side is rotated 90 degrees from the original triangle, they are just going to be a rotated copy of this triangle, right? The relative angle between the velocity vectors is still going to be the same. So this means our included angle, theta, is actually the same in this triangle as well. So I think now that we have some intuition behind it, I'll just make the triangle nicer here. So we said that maybe we have a velocity vector v. I'm just getting rid of the arrowheads to make it look nicer. And the side we were interested in was this delta v. And again, I'm just doing tip to tail addition here. All right, so why are these triangles similar? Well, the triangles are similar because they have two identical sides, right? R and R, V and V, and the included angle theta is the same, so they're included by side angle side. We can derive this result without any geometry if you're a calculus guru. You can figure out what the equations are of circular motion and do some calculus, but we're going to practice our geometry skills here. So using the similar triangles, we're going to figure out that this is the radial acceleration, which is centripetal acceleration. So since these triangles are similar, their ratios of sides across triangles should be the same. So for example, the side across from the angle, delta S, divided by one of the other sides, would be the exact same result as delta V divided by V. Because when we have similar triangles, I can say across from theta divided by adjacent to theta equals across from theta divided by adjacent to theta. And we are going to be interested in acceleration, which is delta V over delta T. So maybe let's solve this for delta V. So delta V would be equal to V over R times delta S. And we're getting close, but we don't have acceleration yet. So remember, acceleration is equal to delta V over delta T. So let's just divide both sides by delta T. Let's put that in a different color so I show that it's something that I did. So we get delta V over T, which would be the acceleration, magnitude at least. We get V over R, and then we have position divided by time, which is, of course, speed or velocity. So acceleration is V squared over R. Exactly the result we wanted to derive. So that was kind of theoretical, but at least we've proven this result. So we have proven that acceleration in a uniform circle is V squared over R. So anytime you're turning at all, this would be the not radial. I'm so bad at that. This would be the, this is the radial component. All right, centripetal. All right, a car traveling along a flat road reaches a curve. The car is turning at points A and B and is not turning at point C. We want to consider the following scenarios. The car moves at constant speed. The car moves at an increasing speed. The car moves at a decreasing speed. We want the total acceleration of the car at point A in each scenario. So it does say that the car is turning, and the speed of the car is the same at all 3 points. So we actually know that there are going to be two acceleration components here. There's the radial or centripetal acceleration, v squared over r. And then there's the tangential acceleration, which is just equal to speed divided by time. That's your speeding up, slowing down acceleration. I think we can make this more clear by saying this is like velocity speed change. Divided by time. And these are, of course, vector components. So for A, or scenario 1, we're moving at a constant speed of 12 meters per second. So this would be only centripetal acceleration because the car is only turning. It's not speeding up or slowing down. Here, the car is turning at that speed and speeding up. So we have A perpendicular and A parallel. And same idea for the slowing down. So if we were to do our ranking, we see that there's only one component of acceleration for scenario 1, and there are two components for scenarios 2 and 3. It doesn't matter that we're speeding up in one and slowing down in the other because they add as vectors. So we said this is a Pythagorean theorem situation. because the tangential acceleration will be tangent to the path, the radial will be perpendicular, so it doesn't matter which way this vector is, they're going to make a right triangle regardless. So A is the least, or 1, sorry, scenario 1 is the least, and then 2 and 3 tie. So we do have the same centripetal acceleration magnitude in all three scenarios, but in scenarios 2 and 3, there's also tangential accelerations of the same magnitude to deal with, so we make the same right triangle. And of course, a right triangle is always going to be longer than just one of the sides, the hypotenuse at least. All right, let's draw qualitatively accurate velocity and acceleration vectors for the car at A, B, and C in each scenario. Well, scenario 1, this is just turning at a constant speed. So we have tangent for velocity, tangent for velocity, tangent for velocity. Try to make it roughly the same. And then for their acceleration, it would be towards the center exactly, towards the center exactly. And it does say they end their turn before reaching point C, so there should be no acceleration there. Then for scenario 2, so this is the speeding up. So scenario 2, I know we can't accurately show it, but just to kind of get a sense of things. We know they are still turning on this path. I'm just going to show their velocity sort of getting larger. Now, we do know that there will be a radial acceleration component, just like last time. So this will definitely be part of the acceleration. But they're also speeding up. So what we know is that there also needs to be a tangential component along the path. So the acceleration must partially agree with these vectors. So we know it's going to be partially turning and partially speeding up. So I'm just going to do something maybe like this. It's not going to be nice and clean. It's going to be at some sort of an angle. Same thing here. It's going to be at some sort of an angle. And then depending on whether we think the car stops accelerating or not, at point C, it'll depend. But if the car is still just speeding up at a constant rate, then its acceleration will be purely tangent when the turning stops. Then for the slowdown, it is just going to be the inverse. So we're moving tangent, but slower, and we're moving tangent, but slower. So they are turning, but they're also slowing down. So we're going to have something like this. We are turning, but we're also slowing down. So it's going to be something like this. And we could still be slowing down. So I'm going to do that. That's kind of tricky. The speeding up and slowing down ones, of course, because it's not just purely centripetal. Suppose at point A, the radius of curvature of the car's path is 40 meters. Let's calculate the centripetal acceleration at point A. So centripetal, the only things that affect centripetal acceleration are speed and path radius. The car's speed was 12 meters per second. And there's no chance this is a nice number. I'm sure it's just a small decimal. This is 3.6 meters per second per second. And then we want the magnitude of the car's total acceleration in scenario 2 at this point. So what we said is that there's definitely going to be a turning acceleration of all three cars at that point of 3.6 meters per second squared. But also, in scenario 2, we have the car speeding up tangentially at 1.5 meters per second squared. So, if we were to look at what this could look like, this could look like the circles. Like this represents your circle. They could have They could have a 3.6 meters per second squared component. And they could also have a 1.5 meters per second squared component. So the net acceleration would just be the tip to tail addition of those and then Pythagorean theorem. Awful triangle from me there. So acceleration is just the square root of the sum of the squares. And I see why I picked these values. What Pythagorean triple is this? Pop quiz. This would be a sibling of the 5, 12, 13, I'm pretty sure. Because we get 3.9 meters per second squared. And now to end with this little car question, physics teachers often joke that if you use the definition of acceleration, you can actually say your car has 3 accelerators. Justify this claim. Well, acceleration is rate of velocity change, which is speed plus direction. So anything that changes the speed or direction of your car counts. So of course, we have the gas pedal, which speeds you up. We have the brake pedal, which slows you down. And we have the steering wheel, which changes your direction. So we could increase the magnitude of V, we could decrease the magnitude of V, or we could change the direction of V. So that is why we joke that there are many accelerators in your car. So since we have an acceleration, we have a force. So the rest of this will be discussing forces that are causing objects to move in circular paths. So applying Newton's laws to a circle, we do know that the net force is equal to mass over mass times acceleration. So any net force in the radial direction can be set equal to mv squared over r, because we just tack on an m to our acceleration term v squared over r. So this is not a new force or anything. All our old forces totally work to supply a centripetal acceleration. So whatever forces are causing your net force or causing your circular motion, you just set them equal to mv squared over r. So this is known as a centripetal force because it is a force that causes an object to move in a circle, but it is not a new force. This is an adjective, not a noun. Right? It's not like normal force, which is an actual force. Centripetal, I always think of it as an adjective. It describes a property of a force, just like net. Net force is not a type of force. It's an adjective describing a force or a collection of forces. So it can be a force, it can be a component, or it could be a subtraction or addition of forces that can combine to give you a radial net force. So our general strategy is, of course, draw the free body diagram. Do not include centripetal force on the diagram. That's not a force. But what you can do is you can figure out who is causing the centripetal force, because there will always be a force directed towards the center of the circle, or a combination of forces, or a component, and that is your centripetal force supplier. And once you figure out F net using help minus hurt, you can set that equal to mv squared over r in the radial direction. Again, radial means with the circle radius. So first we'll start with just the turning car. So suppose a car is traveling through a roundabout of radius r. There's a coefficient of static friction mu between the tires and the road. We'll get into this much later. I'm just going to tell you this is a fact that tires and wheels are actually stationary relative to the ground at the contact point only, so it's actually static friction involved with the tires. That's not clear. I'm just going to, we will figure that out a lot later when we talk about rotating, but we need it for this problem to know that it's static friction. So let's draw the forces exerted on the car at the position shown. So let's draw it right on here. So we definitely know that we have our usual gravitational force, and then the car is just on a flat road and it's not accelerating into or out of the road. So we do know that there are going to be equal normal and gravitational forces. But we also know that the car is turning towards the center of the circle. So there is going to be an acceleration towards the center of that circle, meaning there must be a force supplying that acceleration, because Newton's second law. If there's an acceleration, there is a net force. And there's no net force right now because normal and gravity are balanced. And based on the problem setup, the fact that I explicitly gave you the static friction coefficient and did all of this discussion about static friction means that there is going to be a static friction force, and it's actually exerted on the tires and points towards the center of the circle. So we can draw that where we have our gravitational force, we have our normal force, and then we are going to have a static frictional force that supplies our centripetal force. Make you purple because that's going to bother me. So identify which forces or force components contribute to the net centripetal force exerted on the car. Well, the top of the circle is not up or down, so it's not those forces, so that only leaves static friction. And it is the full static friction, because all of static friction is pointed towards the center of the circle. There exists a maximum speed the car can travel around the circle without slipping out of its trajectory. So lots of times with these circular motion, there's problems. There will be some limiting cases, and that's going to be due to some constraint on the forces. So why could there possibly exist a max speed the car can go around the circle without slipping out? Well, who is causing us to go in the circle? It's static friction. What do we know about static friction? It has a max value. So if the car is going really, really, really fast, and we do know that the perpendicular net force is mv squared over r. So if you go faster and faster and faster and faster, the force required to keep you in that circle is going up and up and up and up. And eventually static friction can't do it because static friction has a max value. So if the car travels too quickly, the required centripetal force that would keep you in the circle is larger than Fs max. So the car would not continue going in the circle and it would begin to slip. So let's find this slipping speed. Well, we asked the conceptual part first, so we know that the cutoff happens when the maximum value of static friction is reached when supplying the radial net force. So static friction's maximum value is mu s times normal force. The net force in the perpendicular direction of any object is just mv squared over r. And we also know that this car is just on a flat horizontal road, not accelerating that way, so Fn is mg. So we can do some rearranging now. We see that everybody brought mass, so we get mu g is equal to v squared over r. So v squared would be equal to r mu g. So the maximum speed you could go would be the square root of r times mu times g. Rug. When the road is icy and therefore more slippery, the maximum speed the car can travel around the roundabout decreases. That's another just driver's ed thing, right? We know that you can't take a turn as quickly as you want when the roads are slippery. So why does that happen qualitatively? Well, if the road is icy, that's going to change the friction coefficient, and it's going to be lower. So if you have a lower friction coefficient, you can supply less static friction as a maximum value. So you would achieve Fs max at a lower speed, and thus you can't go as fast as before. So a lower static friction lowers the maximum possible centripetal force from the ground, so a lower maximum speed is possible. And then justify using our expression from part C. Well, our expression from part C says that the max speed we can go is square root of r times mu times g. So as mu decreases, v max also decreases because everything is in the numerator. So we have a direct correspondence here. This is actually one of my favorite mechanics problems. This is a case of circular motion involving an amusement park ride. This is just known as the Gravitron problem. So this is a spinning amusement park ride where riders stand against the inside of a wall of a large cylinder, and then the ride spins up and up and up and up and up and up, and then the floor drops out, and the people are magically stuck to the wall. So the person has mass m, and there's a coefficient mu of static friction between the person and the wall. So let's draw and label the forces exerted on the person once the floor has dropped out. So they are just floating there. Well, the force we can get for sure, of course, we know it. It's gravity, Fg. And what is preventing them from falling? Well, it's not normal force, because normal force is directed perpendicular to the surface. So normal force is actually here. So maybe we can draw normal force there. Because we can always get the direction of normal force because it's just out. So what is preventing the person from sliding down the wall? Well, the person is being prevented from sliding. Prevented from sliding, that's friction, and more specifically, static friction. So, which forces and force components contribute to the net centripetal force exerted on the person? Well, the person is rotating in a circle, so the center of the circle is this way. The only force that acts radially is normal force. So it is the full normal force. There exists a minimum speed, V min, of the ride, such that the person remains stuck to the wall. So, why is it the case that if the ride moves too slow, the person won't get stuck to the wall? Well, why are they stuck to the wall? They're stuck to the wall because of static friction. And static friction is less than or equal to the static friction coefficient times normal force. So, this normal force, which is the wall pushing the rider, increases with speed because we know that perpendicular net force is mv squared over r. So, a faster ride means a greater centripetal force, means the wall pushes harder on the person, meaning there is a larger normal force and therefore a larger frictional force. So, the normal force supplies that centripetal force, meaning the normal force increases with the speed of the ride. And since static friction's value is proportional to normal force, if the ride's speed is too low, then the maximum value of static friction is not large enough to balance the weight of the rider. And apparently that's not red anymore. Cool. So let's derive an expression for this minimum velocity that the ride needs to go. So we do know that the normal force is supplying the radial net force. So this means the normal force is equal to mv squared over r. That's all we can do with that one right now. But we also know that if the rider is balanced against the wall, static friction's maximum value can support them. And I'm saying Fs is Fs max because we're looking for this cutoff speed, V min. So I can just set Fs equal to mu s times normal force, and Fg is just mg. And we said that the normal force was equal to mv squared over r. So mass cancels, right? Everybody brought mass. So we get v squared would be equal to g divided by, would be gr divided by mu. So the minimum velocity required would just be the square root of that. All right, derive an expression for the highest possible period of revolution such that the person remains stuck to the wall. Well, we can just use the constant speed relationship, that distance equals speed times time, and distance is just 2 pi r. So the highest possible period of revolution, that would mean the longest it would take to revolve. So the longest revolution is achieved by the lowest velocity. So T max would just be equal to 2 pi r divided by the V min from earlier. So that'd be 2 pi r divided by square root of gr divided by mu. So we'd get a 2 pi in front, and then we'd get a square root. You could just box that, by the way, and it's fine. 2 pi square root mu over gr, I think. No. Square root mu r over g. So that will be our period. And this should make sense that this is our period expression, because if you have a larger mu value, that means that the required speed is less, so the max period is higher. So this is our expression for the period. All right, let's sketch a graph of the magnitude of the frictional force exerted on the rider as a function of the ride's speed, or faster than the minimum. So what we know is that if the rider is stuck to the wall, then this just means that the frictional force is equal to the static friction force, which is equal to the weight mg of the rider. So yes, it's true that as the V goes up and up and up and up, the normal force goes up and up and up, so Fs max goes up and up and up, but the static friction force only has to balance what it has to balance, which is just mg. So the ride can go as fast as it wants. That person still is just remaining stuck to the wall with that constant static friction force mg. Now, there would be some sliding down the wall kind of happening if it was less than Vmin, so I did make a decision to not actually include that region, but I'm fairly confident that the kinetic friction regime, or the static friction force, even though it wouldn't act forever, we just graphed Fs would look like that. Static friction force would look like that, because then you get the quadratic increase with normal force. In terms of Vmin, determine the new minimum speed of the ride required if we half the radius, double the coefficient, double the mass. Okay, this is our expression, square root gr over mu. Let's space it out more because we're going to do multipliers. All right, so radius of the ride is halved. Well, mu doesn't change. R is the only thing that changes. It gets halved. So my Vmin would be halved, but it's under a square root. So this would be the square root of 1/2, or 1 over square root of 2 Vmin. Coefficient of friction is doubled, so we can do the same thing. It is the same general formula. So we're just doubling mu. So that doubles. So the denominator doubles. So it is 1 over root 2 again, because we have divide by 2 under the square root. And then the mass of the person is doubled. Well, there's no mass in this formula. So V min does not depend on M. So this means it's still V min. So that's interesting for the amusement park design perspective of this. So when designing this minimum speed, it actually does not depend on the masses of the person that will be riding it. So you can make this sort of universal speed. Now, of course, you're going to make it much bigger than this for accounting for sort of errors, but it does not depend on the mass of the rider. Now we have a vertical circle to deal with. So we have a bucket that's attached to a string of length 0.5 meters. So the length is 0.5 meters. The mass is 2 kilograms. Person then swings the bucket in a vertical circle as shown. In 3 separate trials, the bucket passes through each of the indicated points with a speed of 3 meters per second. Kind of weird wording by me. I just said it because it's saying the swings at constant speed is not realistic. So we're just saying they swung it at one point. We swung it at 3 meters per second through this point. Then another time we swung it through this point at 3 meters per second. Then at another point we swung it at this point at 3 meters per second. So we want to rank the tension eventually in the string at each of these points. So let's figure out the forces exerted on the bucket at each of these points. And we want to indicate who is causing the centripetal acceleration. So what we know is that the perpendicular or radial acceleration is caused by this force, is equal to mv squared over r. Since we have the same speed and the same radius, this is the same at all 3 points. So our net force must be the same magnitude and always directed towards the center of the circle. So we'll start just with the weight of the bucket. That's going to be the same at all 3 points. And then at point A, that's going to be pulling us upwards. So I'm going to show that we have a long tension there, Ft. And that gives us 2 units of net force towards the center of the circle. Then at point B, bucket is over here, so the string pulls us this way. And there's only 2 units of tension required here to get us 2 units of net force towards the center. And then at point C, we're at the very top. If we're at the very top, we're getting pulled down. So what downward pull do we need to get that? Well, that's just going to be 1. Well, so here, what's supplying the centripetal force? Tension minus weight. What's supplying the centripetal force here? Tension. What's supplying the centripetal force here? Tension plus gravity. Weight. Rank the magnitude of the tension in the string at each of the indicated points. Well, our diagram made this work because we do have the same net force towards the center of the circle at all 3 points as we expect. So we can just use our drawing here and we see that tension was the lowest at C, it was the middle value at B, and it was the largest at A. So why did this happen? Lots of words here. The speed of the bucket is the same at each point. So the net centripetal force must be the same in magnitude. So at point A, there's 2 forces fighting for control. So you got to pull a lot harder with tension to counter the gravity. So that's why that's the biggest tension. And at point C, gravity is helping the tension supply the centripetal force. So tension doesn't have to be as long. In point B, gravity is neutral relative to the tension force. So that's why it's the intermediate value. So now let's calculate the tension in the string at each of the indicated points. So to start, we do know that the net radial force is just mv squared over r, which is 2 times 3 squared divided by 0.5, because the speed was 3 meters per second, mass of the bucket was 2 kilograms, string length was 0.5 meters. Let's see, what is this going to be? It's going to be 4 times 9, 36 newtons. So the net force must be 36 newtons in each case. All right, so at point A, centripetal force is supplied by the difference between tension and weight. So 36 is equal to, let's call this TA, just to be consistent. Is TA minus the weight mg of the bucket, so 20. So TA would be 56 newtons. Then at point B, the perpendicular net force is being supplied just by tension itself. So TB is just that centripetal net force we needed, 36 newtons. There's no addition or subtraction. And then point C, perpendicular net force is given by the sum of the weight and the tension force. So 36 is equal to mg plus tension. So TC is equal to 16 newtons. So we do see that the tension is the largest at A and the lowest at C, as our ranking indicated. Now, this is the vertical circle case to know. This is very important, shows up all the time. A block slides along a frictionless surface through a vertical loop of radius r. The block remains in contact with the loop throughout the entirety of its motion. Draw and label the forces exerted on the block at each of the indicated points. Indicate which forces and force components contribute to the centripetal force at the given location. All right, so just kind of diagramming this out. We know that for sure the block is going to have weight G directed downward at each of these points. Then the only other force we could have would be the normal force, because the only other thing we have is a surface. So, kind of just knowing what needs to happen here, we do know that the center of the circle is up from point A and it's below from point C. So the net force does have to point towards the center of the circle. We'll deal with case B. Also, we do know there will be a centripetal force to the left. So the easiest one to do is point B, because we don't really have to compare these or anything. We just know there's a normal force that way. At point A, the normal force has to push harder than mg, because we need to be accelerating up, right? At that point, we have to be accelerating up to keep us going in a circle. And then at point C, the normal force exerted will be downward. In order to keep us going in a circle. And we could figure out how these values compare and all that, but it's kind of just diagramming it, just to get a sense of the direction. So who's causing the centripetal acceleration here? Well, it's the difference of normal and gravity. Here it's F normal, and here it's F normal plus gravity. So we can see this is essentially the tension question, just with normal force. Let's draw the direction of the velocity and acceleration of the block now. So velocity is super straightforward, because it's just going to be tangent, right? So velocity is just going to be tangent. Now, if we wanted to really look at this, we should think about what's happening to the speed of the block. So when I'm traveling up the loop, this is essentially acting like a curving ramp. So my speed actually should be going down as I go up. So that should be actually noted, that we are slowing down. Go up. And then the acceleration. The acceleration is definitely easiest at at points A and C, because we know we're accelerating up at point A, and down at point C. And then for point B, just use the fact that we drew forces. So point A, net force was up, so acceleration was up. Point C, net force was down, so acceleration is down. But point B, our net force is actually diagonal, so our acceleration is actually diagonal. Because this is not uniform circular motion. The crate is actually slowing down as it goes up the loop. And since it's slowing down, there will be a tangential component of that acceleration, giving us a non-uniform value here. So that's why we don't have just the perpendicular. So this is a really tricky concept. People see circles and automatically think acceleration is always totally perpendicular, but that's only if we don't have speed up or slow down. There exists a max speed of the block at the top of the loop in order to remain in contact. Why is there a minimum required speed referencing the C diagram? Well, of course, we know that to go in a circle, there is a required net centripetal force of mv squared over r. So if the object isn't going fast enough at point C, then that centripetal force is going to be too low. So if the block is moving too slow, then the net centripetal force exerted on the block is not large enough to supply the required centripetal acceleration to continue moving in the circle. So the radius of the circle sort of forces our centripetal acceleration to be a certain value, because just divide by m. So the radius is fixed. So we must have a certain centripetal acceleration in order to make it all the way around. And if you're not going fast enough, you can't get that acceleration from the track. Because the faster the block moves, the larger a push it gets from that normal force. So let's figure out the minimum speed that we need at the top of the loop. Well, the key here is that we're remaining in contact with the loop. So that is our sort of condition, because if the speed is too slow, then the block just falls off the loop, right? Just think about what happens if I place a non-moving thing at the top of this loop. It's just going to fall. So falling means loses contact, which means normal force is 0. So we'll just set up the equation at the top of the loop where the perpendicular force is being supplied by normal and gravity together. But this is the condition where we lose contact. So this is the turning point. So F perpendicular, which is mv squared over r, would be equal to mg. Everybody brought the mass. So we get a pretty well-known result that shows up quite a bit, that v at the top of the loop must be at least square root of gr. So if there's a bigger loop, you need a bigger speed at the top. That makes sense to me. Now we have another setup with components. So now we're going to start introducing components here. This is known as a conical pendulum, where we're just swinging a ball in a circle. We are saying that this mass undergoes uniform circular motion at speed v with radius r due to this setup. All right, what are the forces exerted on the ball at the point shown? Well, of course, ball has weight. And then there's only one other force, and it's tension. And we do know that this ball is accelerating towards the center of the circle, right? So there should be a net force into the circle, but there shouldn't be a net force up or down. So this tension force must at least partially, part of the tension force will cancel the gravitational force, and the other part of tension force will supply the radial net force. So which forces or force components will contribute to the net centripetal force on the ball at that point? Well, it will be the horizontal component of tension. It'll be the x component of tension supplying the centripetal force because the circle is this way and the string is partially in the y, partially in the x, so it's the x component that's dragging us towards the center. What is the magnitude of the vertical component of tension in the string? Well, we just said it. We said that FTY balances FG based on our force diagram. So FTY is equal to mg. So what would be the radial component of tension in the string then? Well, we said the radial component of tension in the string supplies F perpendicular. So this means that FTX is supplying the mv squared over r centripetal force that we need. Right. Derive an expression for tan theta in terms of v and r. So our string looked like this, where we are interested in this angle theta. And we said that the tension force, Ft, has two components. The x component of tension is supplying the centripetal force, and the y component of tension is balancing the weight. So we can just use definition of tangent here to say that tangent of theta is just the opposite over adjacent, which would be the x component divided by the y component. So this would be mg, no, this would be mv squared over r divided by mg. So we would get tan theta is equal to, the m's go away, v squared over gr. So again, all we did here is we used the fact that we knew both tension components and just put them in the triangle. Suppose the speed of the mass is increased while the radius of the circle is held constant. Indicate whether the angle theta increases, decreases, or remains constant. So over here, this is sort of our governing triangle. So we said that we are increasing the speed while maintaining the radius of the circle. So what's happening is that we are increasing the speed. So we're increasing the required centripetal force. So the x component is getting bigger. But also, we're not changing the mass, so the y component stays the same. So that means we're going to get a longer triangle than before. So we'd get something, just to exaggerate, something like that, where our angle is definitely getting larger. So theta gets larger when the speed of the mass is increased because we have a larger centripetal component and the same vertical component. So our triangle is getting wider. And we could easily justify this with part E's expression because we said tan theta. Well, actually, I don't know how easily. We have to know our functional dependence here. We have tan theta equals v squared over gr. So as v increases, tan theta increases. So we know that. And this might be less clear. I would add this to your list of dependencies. You should know how sine, cosine, and tangent behave from 0 to 90. And you should actually also know that as tangent theta increases, this means theta increases. Because the tangent function starts climbing. So tangent is an increasing function. So if the output is increased, the input must also increase. So it does work. All right, last one. This is known as a banked curve, where it's like the turning car, except it is on an angled road. So this is going to do some ramp analysis and centripetal analysis, kind of our last application. It's usually the most complicated, so I left this for last. So let's draw our forces exerted on the car. We're assuming it is frictionless to make the math way easier. We're going to get some weird assumptions out of this, but the frictionless part makes this very manageable. Okay. What are the forces on the car? Of course, mg, straight down. Normal force, out. No friction. Nothing else. These are actually the only forces we get. So, what is happening with this car in the banked road? Well, this is the center. This is the center of the circle. So, what's actually happening is there will be a normal force exerted on the car. And this is going into our next question. And since the center of the circle is over here, we will see that part of the normal force is sending us towards the center of the circle. So the road is actually pushing us out towards the center. The center of the track is sort of over here, far. So part of the normal force is actually going to serve as our centripetal supplier. It's actually going to be the x component of the normal force. Notice that's not something we've been doing, is splitting normal force into x and y on a ramp, which makes this kind of a interesting one-off problem because we have to do some atypical splitting here. The magnitude of the normal force exerted on the car is actually not mg cosine theta. Justify this. So this is like one of the only times the normal force on a ramp is not mg cosine theta, because this is not a balanced scenario. The only thing we know for sure is that the car is going to move at a constant speed, meaning the car is not slipping onto the ramp or up or down the ramp. So what we know is that if we were to draw sort of our component body here, the answer is that the car is accelerating. So since the car is accelerating, the normal force won't be mg cosine theta. But if we go a step further and draw our component body, we know that the car must stay fixed or level on the ramp. So we can actually just draw mg here, because we're not interested with the down the ramp, up the ramp component, because nothing is happening down the ramp or up the ramp. So we can actually see that with our normal force components here, there will be a normal force component that pushes us towards the center of the circle, and a normal force component that is balancing the weight of the car. So that's sort of our component body here, which makes the banked curve just a very strange and atypical situation, because this is the one time we're not actually looking at an object that's sliding up or down a ramp. It's just maintaining its level here. So what is the normal force on the car? Well, we said that the y component of the normal force must equal mg. So we know it's going to be Fn times some trig function is equal to mg. So let's figure out what that is. So if we did some angle tracing here, I'll use my alternate interior trick, where if you draw sort of a Z shape, the angles in the Z's are going to be the same. So what that means is that this angle theta can go right here. So our angle theta can also go there, which means that this angle right here is 90 minus theta. So that's the complement of theta that goes there. So I can write 90 minus theta goes there. So this is actually our theta. It's up there. So this would be Fn cos theta, and this would be Fn sine theta. So kind of a tricky angle trace there. That means that our normal force is just going to be mg over cosine theta, which is notably not mg times cos theta. All right, let's find the speed the car can travel around the banked curve. So we said that the perpendicular radial net force is being supplied by the x component of the normal force. So mv squared over r is equal to Fn times sine theta, right? Fn sine theta was this x component that's actually doing the pushing towards the center. So we can substitute because we said normal force was mg over cosine theta. And we get a sine divided by cosine, which is tangent. So we'd get v squared over r is equal to g tan theta. So v is equal to gr tan theta. And this actually isn't a minimum or maximum speed. This is actually the only speed you can go around an unbanked curve because the normal force is fixed. And that's what's helping supply the centripetal force. So that's why this is not a realistic model, because there's only one magic speed you can go around the unbanked, this frictionless unbanked curve. More reasonable assumption is to say that there is friction. We're not going to do this quantitatively, but we're saying now that there's friction between the tires and the road, indicate whether the maximum safe speed increases, decreases, or remains the same when there's friction present. Well, we want to figure out how the forces will change. Well, if there is friction, that means there will be a component that prevents me from sliding, and part of that will point towards the center of the circle. So we're essentially adding an extra centripetal force, and the normal force is actually going to up well to balance that if there's a downward y component. So V increases when there's friction present because the addition of static friction adds an additional force component that can supply the required centripetal force. Thus, we can supply a bigger centripetal force and therefore have a bigger speed. And here I just talk about this fact that there's actually only one speed that you could go in the non-frictionless case, but we already covered that. Yeah, I think that is legitimately the longest section in the whole course because there's lots of stuff the CED wants us to know about circular motion. So almost all of these cases were explicitly told that these are things we should know. And I think there's some cool problems. So that is circular motion.